So now indeed we have a formula for the spectral radius. But this formula is not always terribly helpful, maybe even handy, because you have to compute these large powers of A and then the norms and then the nth root. So it sounds like a lot of work. And our question is, can we single out classes of operators A where the result of that formula is something simple as just the norm of A? Or in other words, can we say for which operators the red and the green circle are in fact the same? Well, obviously not for that one, but maybe we find some. And to do so, we now go to Hilbert space so that we can talk about the adjoint operator of A. And then here is a first class where we think, yes, the spectral radius may be the norm of A. Let's try self-adjoint operators, which means operators A for which the adjoint is A itself. And we want the adjoint because we want to work with the following formula. The norm of A star times A is the norm of A and then squared. The square is outside. And let's label that one with, number must be 1. And we know it from one of our exercise problems. Okay, and now let's try and play around with that formula 1. And at the same time we have the condition A star equals A. Well, let's start with this copy of equality 1. And then just substitute A for A star here. And that's already something, because it tells you that the square, which used to be inside the norm, can actually be moved outside. And then if you could do that with every n, then in the end, the nth root would just remove the power n and you would just be back to norm A. Well, let's see whether that actually works. And let's not try n equals 3, but instead n equals 4, because we can roll back to n equals 2 from there. So the norm of A to the power 4. And now let's play again with self-adjointness. And let me write down A to the power 4, but for these two of the factors I write A star instead of A, because it's the same. Okay, now this here is just A squared, and this here is just A star squared, but we could also say A square and then start. Because the adjoint of a product is just the product of the adjoints in reverse order, but who cares about the order when everything's the same? But now here we are back to the left-hand side of equality 1, only with A square in place of A. So we can just copy the right-hand side, but with A square in place of A. And now this is what I meant before, because we are reducing everything to the norm of A squared, which we did here already. So we should get that, we should give that equality a label also. That must be label number 2 then. So by number 2, we can write norm A and then squared instead of norm of A squared where the square is inside. And let me use different colors here, because the argument is just for the blue part, where we use equation 2 and get this new blue part where the square comes out of the norm. But we should not forget about the other square, which was still outside here, which is now giving us the 4th power of norm A. So indeed also a 4 can come out of the norm. And that's essentially how you proceed. So the next thing you would do is just repeat the argument for A to the power of 8. Then you repeat the construction, reduce everything to this equality for the norm of A to the power 4, and so on. So you get that you can drag the exponent n outside of the norm. But our proof shows that this happens for 2, 4, 8, and so on. So for the powers of 2. And now it's time to take the nth root. So we get nth root of this norm a to the power n here and just norm of a over here. But that's just the expression that we denoted by little r sub n before. And we should keep in mind that this equality holds only for powers of 2. But the spectral radius formula says that this sequence converges to the spectral radius of A. And we might not know the whole sequence, but we know the subsequence here. And if we know it converges, then the limit must be the same limit for the subsequence. And this is obvious because it's a constant subsequence. So the answer must be norm of A. Okay, excellent. So for self-adjoint operators, the spectral radius turns out to be just the norm of A. Can we find other, maybe larger classes for which this is still true? Yes, we can. And this larger class is the set of all normal operators. And I hope you recall from your linear algebra course what a normal matrix is. It means the same for operators. It just means that A and A star commute. So it doesn't matter whether you multiply them in this or in that order, you get the same. Okay, well, obviously that is a generalization of example number 1, because if you're self-adjoint, then obviously this equality is true. Well, of course, you could ask, well, why did you talk us through self-adjoint operators if it's going to be covered by what you say in number 2 anyway? And I'll say, well, because we wanted to learn how to argue before we do the tricky stuff. And the argument is quite, well, for large parts the argument is the same, but obviously not so easy up here. So we have to work with this equality, and yeah, let's try and play with it. This is actually not easy. Yeah, do you remember when I said if you want to prove something, then you just start with your left-hand side and transform it, and then maybe at the other end of your sheet of paper you start with the right-hand side and transform it back, and then you keep fingers crossed that somewhere in the middle you will meet. This is not what we're going to do now. What we're going to do now sounds even crazier. We're going to start in the middle. We don't know where we come from, we don't know where we want to go to, but we know what we want to use in the middle. We want to use this. So let's now prove by starting in the middle. Okay, now actually that's still too simple to get something useful out of it, so we have to make it a bit more complicated. How about that? Okay, of course that's still true. Now the right-hand side can be written like we did before, so we just put a square here and a square star here. And then if we put norms everywhere, we can again use equality number 1. Where is it? Up here. But now again with a square in place of a, we get the right hand side of number 1, but with a square in place of a. Okay, that was not so bad. Now let's walk from the middle towards the left, and let's see what we can do with this expression here. And for this argument, we're going to use that a star a in brackets star is just a star and then a star star. So you take the adjoints and reverse the order, but a star star is just a. Okay, so in place of a star a, which is here, we can just write a star a brackets star. So we replaced this here by this. But now we are again in the situation of equality 1, which is clearly the hero of the day, because we have the left-hand side of 1 with a star a in place of a. So let's just write the right-hand side of equality 1 with a star a where there used to be a. And now, come on, we're again in the situation of equality 1, just with a little square outside. So let's apply equality 1 to the red bit here. And then you get norm a squared, and the blue square is still here also. Okay, what a ride. Now we're almost finished. Let's just take the square root on both sides. And what we get is norm a squared with a square outside from here equals norm a squared with a square inside from here. So indeed we can again drag the square outside the norm if a is a normal operator. Now you don't have to be scared for how the same argument looks for the power 4. It's not difficult if you do it clever. So the next thing you do is just to put b, which is your shorthand for a squared, in place of a in this equality. Now this equality was derived from the assumption that a is normal, so b should better be normal. And please check for yourself whether that is true. So for better reference, let's label this last equality by number 3. And then we start from here, only that we write b instead of a. But b is just a squared. So we get norm of a squared squared over here, which is just norm of a to the power 4. And on the other side, we get norm of a squared and then squared outside. But for the red bit, we again apply number 3, which brings this square out here. And we shouldn't forget about the black square. So that on the left, we happily arrive at norm a to the power 4. And the power 4 is already outside. So we can get the exponent 4 from inside to outside, and the only assumption is that a is normal and hence a square is normal. Okay, now it's clear how to proceed. You're using this formula and you again substitute a squared for b, and then you get the same with exponent 8 and so on. So again, you see that you can drag the exponent n outside the norm if n is a power of 2, and then by taking the nth root, you see that our sequence Rn, which is just nth root of norm of a to the power n, is only the norm of a, and again you use that this converges to the spectral radius, so also this subsequence should converge to the spectral radius, but it's constant, so this constant must be equal to the spectral radius. Excellent. Job done. Now you see that's what you call algebra. You're just playing around like a child with A's and stars, and you're trying and you're using actually only one rule, which is this, until you prove something substantial. Right.